Good day, everyone. This is Mabel M. Lolo from Section R, and I'm going to report to you the plate number 10, problem number 1, letter C. So in this problem, we are asked to find the load combination of axial load capacity and moment strength for the tied column with the following condition of steel strain, which is equals to 0.003. So we have here the cross-sectional drawing of tied column and the stress strain diagram. So since our section is symmetrical, our plastic neutral axis is going to be at the mid-length of 450 mm, or the D, which is, as you can see the line, this is the PNA. First things first, we need to find the value of C and A that will be used in getting the steel force from different steel layer. So by ratio and proportion, we have the 0.003 for the epsilon s over D minus C equals to 0.003 over C. So rearranging this, we'll have the value of C equals to 225 mm and 48, which is equals to 191.25 mm. Now that we have the value of C and A, next is we need to determine the steel forces from the different steel layer of the tied column. So we have here the Fs with the formula of Fs equals to 600 times the quantity of D minus C over C, and substituting all the values, we have obtained the value of Fs as 600 MPa. So since our value for Fy is 420 megapascal, then we will be using the value of Fy since it exceeds Fs exceeds the value of Fy. So next is Fs1, Fs2, and Fs3. So the same formula in getting those values, substituting them, we have the value of Fs1 as 266.67 megapascal for the Fs1, 66.67 megapascal for Fs2, and 400 megapascal for Fs3. Now let's move on in the determining the bar area. So we have here the formula of pi times the diameter of the bar, which is equals to 25 squared divided by 4, and 1 bar is equals to 490.874 mm squared. And for the 2 bars, we have 981.75 mm squared, and for the 3 bars, we have 1472.622 mm squared. Next is to find the component of our compression steel and compression concrete. So we have here C sub C equals to 0.85 FC prime AB, and substituting of the values, we obtain the value of CC as 1,365,525 Newton. For the CS2, we have here equals to AS2 times FS2, which is equals to 981.75 times 66.67. We obtain the value of CS2 as 65,453.27 Newton. And for the CS3, we have here equals to AS3 times FS3, which is equals to 1,472.62 times 400. Then we obtain the value of CS3 as 589,048.8 Newton. And for the T, we have the formula of T equals to AS times FS, which is equals to AS is 1,472.622 times FS is 420. Going back to our previous solution, we have the value of Fs of 600 since it exceeds the value of Fy. So instead of using 600, we will be using the value of Fy as, which is equals to 420. Then the value of T is equals to 618,501.24 Newton. And for the value of T sub 1, we have T sub 1 equals to AS1 times FS1. And then substituting the values, we obtain the value of T sub 1 as 261,803.2775 Newton. Next is to sum up forces vertical, which is equals to 0. So we have here the Pn, or the nominal load, equals to C sub C plus CS2 plus CS3 minus T sub 1. Then substituting all the values, we obtain the value of nominal load as 1,139,722.558 Newton. And then for the sum up moment at T equals to 0, we have nominal load times its moment arm, 187.5 plus E equals C sub C times the quantity of D minus A over 2 plus CS2 times 250 plus CS3 times 375 minus T sub 1 times 125. Substituting all the values, we obtain the value of E as 416.54 mm. And since Fy is less than Fs, which is less than also to 1000 MPa, our reduction factor formula will be 0.65 plus 0.25 times Fs minus Fy over 1000 minus Fy. So substituting all the values, we obtain the reduction factor as 0.728. So that would be all. Thank you for listening and have a nice day.